Welcome to US. Today we discuss about the basic fabrication process steps of VLSI chip. In this fabrication process, the first step is the vapor preparation, and second one is the photolithography, and next one etching, next one oxidation, next one thermal diffusion, ion implantation, deposition, epitaxy growth, and metallization. And first step is the vapor preparation. How to prepare the vapor? In the vapor processing, it is using the Joe-Kralski method is using this vapor preparation. The basic raw material used in modern semiconductor plants is a vapor or disk of silicon, which varies from 75 mm to 150 mm in diameter and is less than 1 mm thick. Vapors are cut from ingots of a single crystal silicon that have been pulled from a crucible melt of pure molten polycrystalline silicon. This is known as Joe-Kralski method. Controlled amount of impurities are added to the melt to provide the crystal with required properties. The crystal orientation is determined by a seed crystal that is dipped into the melt to initiate single crystal growth. The melt contained in a quartz crucible which is surrounded by a graphical radiator. The graphite is heated by radio frequency introduction and the temperature is maintained a few degrees above the melting point of silicon. It's approximately equal to 1425 centigrade. The atmosphere above the melt is typically helium or argon. After the seed is dipped into the melt, the seed is gradually withdrawn vertically from the melt while simultaneously being rotated. The molten polycrystalline silicon melts the tip of the seed and is withdrawn. Refreezing occurs. As the melt freezes, it assumes the single crystal form of the seed. This process is continued until the melt consumed. The diameter of the ingot is determined by the seed withdrawal rate and seed rotation rate. Growth rate ranges from 30 to 180 mm per hour. Slicing into vapors is usually carried out using internal cutting edge diamond blades. Vapors are usually between 0.25 mm and 1.0 mm thick, depending on their diameter. Ingots are then sawed into vapors approximately 500 to 1000 micrometer, that is 0.5 to 1 millimeter thick, using a diamond tipped saw. It is called vapor sawing. Photolithography process. In this photolithography process, first of all, we applying the photoresistive material on the surface of the substrate, and next step is a soft bake, that means drives of solvents in the photoresistive, and third step is the expose the photoresistive layer to UV rays through a mask layer. That means by using masking layer, UV rays is applied on the substrate material. And next one is the develop, that means remove the unwanted photoresistive layer using solvents. And next up is the hot bake, that is greater than 100 centigrade. And next step is the remove the photoresistive layer by using solvents events. The process of exposing selective areas to light through a photo mask is called printing. The types of printing includes contact printing, proximity printing, projection printing. Photography process in this we using generally two types. One is the positive photoresistive layer, and we using the positive photoresistive layer, and another one is the negative photoresistive layer. In negative photoresistive layer is hardened against the developer by the UV radiation, and hence the remains on the surface where UV shown through the mask. If positive photoresistive, which is initially insoluble and becomes soluble after exposure to UV light, is called positive photoresist. Etching. Etching is the process of selectively removing a layer of material. When etching is performed, the etchant may be remove portion of the desired material, or the underlying layer, or the masking layer. There are basically two types of etches. One is the wet etching, and second one is the dry etching. Wet etching, which uses the chemicals, and dry etching, which uses chemically active ionized gases. And next step is the oxidation. Oxidation is a process by which a layer of silicon dioxide is grown on the surface of a silicon vapor. Requires only substrate heating to 900 to 1200 centigrade in a dry or wet environment using an oxidation furnace. And next step is the diffusion. Diffusion is the movement of impurity atoms at the surface of the silicon into the bulk of the silicon, always in the direction from higher concentration to lower concentration. Diffusion is typically done at high temperature, that is 800 to 1400 centigrade. And next up is the ion implantation. Ion implantation is the process by which impurity ions are accelerated to a high velocity and physically lodged into the target material. Anal is required to active the impurity atoms and repair the physical damage to the crystal lattice. This step is done at 500 to 800 centigrade. Ion implantation is a lower temperature process compared to a diffusion. Can implant through surface layers, thus it is useful for field threshold adjustment. Can achieve unique doping profile such as buried concentration peak. And next one is the deposition. Deposition is the means by which various materials are deposited on silicon vapor. Example is deposited materials are silicon nitride Si3N4, and next one is the silicon dioxide SiO2, or next one is the aluminum, and last one is the polysilicon. There are various ways to deposit a material on a substrate. The type of techniques is using, first one is the chemical vapor deposition, that is CVD, and next one is the low pressure chemical vapor deposition, it is called LPCVD. Next one is the plasma assisted chemical vapor deposition, PECVD, and next technique is the spotter deposition. Material that is being deposited using these techniques cover the entire vapor. And next step is the epitaxy. Epitaxy growth consisting of the formation of a layer of a single crystal silicon on the surface of the silicon material so that the crystal structure of the silicon is continuous across the interface. It is done externally to the material as opposed to diffusion, which is internal. The epitaxy layer can be doped differently, even oppositely of the material on which is it grown. It accomplished at high temperatures using a chemical reaction at the surface. The epitaxy layer can any thickness, typically 1 to 20 microns. And next step is the metallization. First, an insulating glass layer is deposited to cover the silicon, then contact holes are cut into the glass layer down to the silicon. Metal is deposited on the top of the glass connected to the device through the contact holes. The graphic shows the snapshot during the filling of a contact hole with aluminum. The metal oxide semiconductor MOS transistors and related to VLSI technology. There are 4 technologies are using: PMOS, NMOS, CMOS, BiCMOS. PMOS fabrication process. In this PMOS fabrication process, first step is the vapor preparation. In this vapor preparation, there are created series of chemical processing steps involve the oxidation of the silicon, diffusion of impurities into the silicon to give certain conduction characteristics, and depositing and etching of aluminum the silicon to provide interconnections. In PMOS fabrication, a thin vapor cut from a single crystal of a silicon of high purity into which the required N impurities are introduced as the crystal is grown is used for PMOS processing. The processing is performed on this vapor. Such vapors are typically 75 to 150 mm in diameter and 0.4 mm thick and are doped with phosphorus impurity concentration of 10 to the power of 15 cm cube to 10 to the power of 16 per centimeter cube. Such a doping concentration, the vapor has resistivity in the range of 25 ohm centimeter. By total or overall thermal oxidation process, 1 micrometer thick silicon dioxide layer is deposited throughout the vapor surface. The layer used as photoresistive layer acts as a barrier to dopant during the process and to provide a common insulating substrate onto which other layers may be grown. And next step is the surface is covered with a photoresistive layer which is deposited on the vapor and spun to achieve an even distribution of the required thickness. And next step is the photoresistive is then exposed to UV light through a mask which defines those regions into which diffusion it to take place together with the transistor channels. The unexpected portions are subsequently etched away together with the underlying silicon dioxide so that the vapor surface is exposed in the window defined by the mask. And next step is the remaining photoresistive is removed and a thin layer of silicon dioxide SiO2 it's approximately 0.1 micrometer is grown over the entire chip surface. Then polysilicon is deposited on top of this to form the gate structure. In the fabrication of the fine patterning device, precise control of thickness, impurity concentration and resistivity are necessary. And further, photoresistive coating and masking allows the polysilicon to be patterned, and then the thin oxide is removed to exposed areas into which p-type impurities are to be diffused to form the source and drain. The polysilicon with underlying thin oxide and the thick oxide acts as a mask during diffusion. The process is known as self-aligning. Once again, thick oxide SiO2 is deposited over all and is then masked with photoresist and etched to expose selected areas of the polysilicon gate and the drain and source areas where connections. that is contact cuts are to be made. The whole chip then has metal, that is aluminum, deposited over its surface to a thickness typically of 1 micrometer. The metal layer is then masked and etched to form the required interconnection pattern. This is the PMOS transistor now finished. And next one is the NMOS fabrication process. In this NMOS fabrication process, first step is the formation of p-type silicon substrate. That is, in a single crystal silicon layer is doped with p-type impurities are doped into the silicon substrate. And next step is the thick silicon dioxide layer deposited on the substrate. That is 1 micrometer thickness thick silicon dioxide layer is deposited on the substrate. And third step is the thick silicon dioxide is selectively etched to expose the silicon surface on which the MOS transistor will be created. And fourth step is the thin silicon dioxide layer deposited on the overall surface, that is 0.1 micrometer thickness of thin silicon dioxide layer is deposited on the overall surface. And next step is the polysilicon deposited on the top of thin silicon dioxide layer. And next step is the selectively etched to form the interconnects and the MOS transistor gate. The thin oxide layer patterned and etched away to form the source and drain regions. And next step is the N-type doping penetrates the exposed areas on the silicon surface, ultimately creating two N-type regions, source and drain regions, in the p-type substrate. The entire surface is again covered with an insulating layer of silicon dioxide. The insulating oxide layer is then patterned in order to provide contact windows for the drain and source junction. The surface is covered with evaporated aluminum which will form the interconnections. And next step is finally the metal layer is patterned and etched, completing the interconnections of the MOS transistor on the surface. Next step is usually a second and third layers of metallic interconnect can also be added on the top of the structure by creating another insulating oxide layer, cutting contacts, holes, depositing and patterning the metal. Next fabrication process is the CMOS fabrication process. In this CMOS fabrications are 4 types: N-well, P-well, thin tub, silicon on insulator. CMOS means complementary MOS metal oxide semiconductor device. CMOS technology depends on using both N-type and P-type device on the same chip. The two main technologies to do this task are P-well and N-well. In P-well, we'll discuss the process steps involved in this technology. The substrate is N-type. The N-channel device is built into a P-type well within the parent N-type substrate. The P-channel device is built directly on the substrate. In N-well, the substrate is P-type. The N-channel device is built directly on the substrate, while the P-channel device is built into the N-type well within the parent P-type substrate. Two more advanced technologies to do this task are twin tub and silicon on insulator CMOS process, SOI CMOS process, becoming more popular for submicron geometrics where device performance and density must be pushed beyond the limits of the conventional P and N well CMOS process. In twin tub, both an N-well and P-well are manufactured on a lightly doped N-type substrate. In silicon on insulator SOI CMOS process, SOI allows the creation of independent, completely isolated NMOS and PMOS transistors virtually side by side on insulating substrate. CMOS fabrication process. In CMOS fabrication process, P-well produce the balanced performance of P and N transistors. N-channel transistors are faster. Transistors created in a well has less speed compared to one in a substrate. It reduces alpha particle sensitivity. In N-well, it reduces the latch-up condition, low cost, and improved N-channel performance. P-well fabrication process. In P-well on N substrate, in this involve the steps are N-type substrate, then oxidation and mask 1 to create the P-well. It's nearly 4 to 5 micrometer deep, and next step is the P-well doping. In P-well acts as a substrate for NMOS device. The two areas are electrically isolated using thick field oxide and often isolates implants. And next step is the polysilicon gate formation. In this, first step is the remove P-well definition oxide, and next one is the grow thick field oxide, and next step is the pattern, that is mask 2 to expose NMOS and PMOS active regions. Grow thin layer of SiO2 layer, that is approximately equal to 0.1 micrometer gate oxide over the entire chip surface. Deposit polysilicon on top of the gate oxide to form the gate structure. And next step is the pattern poly on gate oxide by using mask 3. And next step is the NMOS P plus source and drain diffusion. This is self-aligning to play to poly gate. Implant P plus NMOS source and drain regions by using mask 4. We implant the P plus NMOS and source and drain regions. And next step is the PMOS N plus source and drain diffusion, self-aligning to poly gate. Implant N plus PMOS source to drain regions by using mask 5, often the inverse of mask 4. And next step is the PMOS N plus source and drain diffusion, contact holes and metallization. Oxide and pattern for contact holes by using mask 6. Next one is the deposit metal and pattern by using mask 7. And passivation oxide and pattern bonding pads by using mask 8 layer. P-well acts as a substrate for NMOS device. To separate substrates, it requires two separate substrate connections. Definitions of substrate connection areas can be included in mask 4 and mask 5. CMOS N-well process. In CMOS N-well process, an N-well process is also widely used. In CMOS N-well process, the basic process steps for pattern transfer through lithography. The fabrication procedure of a single N-type MOS transistor. Now we consider the fabrication sequence of N-well CMOS integrated circuits. The N-well CMOS process starts with a moderately doped P-type silicon substrate. Then an initial thick field oxide layer is grown on the entire surface. The first lithography mask defines the N-well region. Donor atoms, usually phosphorus, are implanted through this window in the oxide. Once the N-well is created, the active areas of the NMOS and PMOS transistors can define. Following the creation of the N-well region, a thick field oxide is grown around the transistor HU regions and A thin gate oxide is ground on top of the active regions. The polysilicon layer 3000 Armstrong is deposited using chemical vapor deposition and patterned by dry plasma etching. The creating polysilicon lines will function as the gate electrode of the NMOS and PMOS transistors and their interconnections. Also, the polysilicon gates acts as self-aligning masks for the source and drain implantation that following this step. Using set of two masks, the N plus and P plus source and drain regions are implanted into the substrate and into the N well respectively. The ohmic contacts to the substrate and to the N well are implanted in these process steps. And next processing step is the advanced CMOS fabrication process steps is the twin step process. It allows separate control over N-type and P-type transistors and also threshold voltage and gain. In twin step CMOS process, this technology provides the basis for separate optimization of the NMOS and PMOS transistors, thus making it possible for threshold voltage, body effect, and the channel transconductance of both types of transistors to tuned independently. Generally, the starting material is a N plus or P plus substrate with a lightly doped epitaxy layer. It's approximately equal to 10 to the power of 15 per centimeter cube on top. This epitaxy layer provides the actual substrate on which the N well and P wells are formed. Since two independent doping steps are performed for the creation of the well regions, the dopant concentration can be carefully optimized to produce the desired device characteristics. In the conventional N-well CMOS process, the doping of the well region is typically about one order of magnitude higher than the substrate, which among other effects results in unbalanced drain parasitics. For inexpensive and low performance chips, one may use a heavily doped substrate and omit one well. The substrate should be doped to about 10 to the power of 16 per centimeter cube with a resistivity of 1 micrometer centimeter. This allows simple construction with good ground potential distribution, but the devices are not optimal and there is a chance of latch up if the voltages are pushed hard. For higher performance chips, one uses a low doped structure 10 to the power of 15 per centimeter cube 10 ohm centimeter and then constructs two wells at optimum doping level called tops in the diagram. Since the substrate is lightly doped, there is less chance for latch up because of the high resistivity. And next processing step technology is the silicon on insulator SOI technology. It uses insulating substrate instead of silicon. Absence of the wells, closer packing of P and N transistors, and low substrate capacitance and possibility of faster circuits, there is no latch up condition is occurred. Silicon on insulator CMOS processor SOI CMOS process. Rather than using silicon as the substrate material, an insulating substrate will improve process characteristics such as speed and latch up conditions. The SOI CMOS technology allows the creation of independent, completely isolated NMOS and PMOS transistors virtually side by side on an insulating substrate. The main advantages of this technology are the higher integration density because of absence of well regions, complete avoidance of the latch-up problem, and low parasitic capacitance compared to the conventional N-well or twin-tub CMOS process. And next technology is the BiCMOS technology. A known deficiency of MOS technology is its limited load driving capabilities due to limiting current sourcing and sinking abilities of PMOS and NMOS transistors. Bipolar transistors have higher gain, better noise characteristics, better high frequency characteristics. BiCMOS gates can be an efficient way of speeding up VLSI circuits. CMOS fabrication process can be extended for BiCMOS. The simplified cross-section of an NPN bipolar junction transistor BJT. The structure consisting of several regions and layers of doped silicon, which is essential from three terminals of the device, that is emitter, base and collector. The NPN type bipolar transistor is fabricated on a P-type silicon substrate. The full bipolar IC, a lightly doped N-type epitaxy layer created on top of the P-type substrate, serves as the collector. The collector contacts region is doped with a higher concentration of N-type impurities in order to reduce the contact resistance. The base region is created by forming a P-type diffusion in the N-type epitaxy layer, and the heavily doped N-type emitter is formed within this P-type base diffusion area. The fabrication process of BiCMOS, and first of all the device cross section of BiCMOS process showing N plus buried layer. And next processing step is the device cross section of BiCMOS processing showing the P buried layer is self-aligning implant. And next process step is the device cross section of BiCMOS process after growth of the epitaxy layer. And next step is the device cross section of BiCMOS process showing epitaxy layer making for N-well implant. After self-aligning P-well implant, previously the N-wells are implanted and 350 nanometer oxide is grown, which serves as blocking mask for the P-well implant. Device cross section of BiCMOS process showing the channel stop implant before the vapor was planarized and patterned. A deep N plus subcollector implant, the PMOS and NMOS device are protected by the photoresist. It shows the intrinsic base implant. The device cross section of BiCMOS process showing the fabrication of the polysilicon emitter. The emitter window is opened, followed by the polysilicon deposition. The polysilicon is implanted and will serve a out diffusion source to form the emitter junction. Before the NMOS LED doping is implanted, the subcollector is opened to collect additional N-type doping. The source and drain implantation of the NMOS device, again phosphorus is implanted into the subcollector region. The PMOS source drain implantation, which is also applied to the base to form the extrinsic base doping. The device cross section of BiCMOS process after fabrication of the active areas. The source and drain angle is optimized to emitter of diffusion conditions. Afterwards, the structure is scheduled for a double level interconnect process. Comparison of CMOS and bipolar technology. In CMOS technology, it's having the low static power dissipation, high input impedance, that is low driving current, scalable threshold voltage, high noise margin, high delay sensitive to load, that is fan out limitations, and last one is a near ideal switching device. In bipolar technology, high power dissipation, low input impedance, that is high driving current, and next one is the low voltage swing logic, low packing density, low delay sensitivity, and essentially unidirectional. N-well BiCMOS fabrication processing steps, the additional steps also is required compared to a single metal CMOS. That is, first step is the form N-well, and next one is the form buried N plus layer, and next one is the delineate active area and channel stop, threshold voltage adjustment, form the deep N plus collector, delineate poly and gate areas, form N plus active areas, form P plus active areas, and form the P plus base for bipolar, define the contacts, and delineate the metal areas. Production of E-beam mask. This technique is used for a geometrical dimension shrink to allows for the processing of a number of different chip designing on a single wafer. Processing steps. Starting material consisting of chromi plated glass which are coated with an E-beam sensitive resistive. E-beam machine is loaded with the mask description data. Plates are loaded into E-beam machine where they are exposed with the pattern specified by the customer mask data. After exposed to the E-beam, the plates are introduced in the developer to bring out the pattern left by the E-beam in resistive coating. The chromi is then etched and the place is stripped of the remaining E-beam resistive. The advantages of E-beam masking is the tighter layer to layer registration and smaller feature size. There are two approaches to the E-beam mission. One is the raster scanning and then one is the vector scanning. Raster scanning. The electron beam scans all possible locations and a bitmap is used to turn the E-beam on and off depending on whether the particular location being scanned is to be exposed or not. Vector scanning, the beam is directly only those locations which are to be exposed, but we will maintain the data. Thank you.